All right, so picture this. It's 1955, and somewhere in a Caterpillar boardroom, probably in Peoria, Illinois, an engineer is standing in front of a conference table. He's holding photographs. And the men sitting around that table, they're staring at these images with expressions that range from disbelief to, well, let's call it professional concern. Because what they're looking at shouldn't exist. Can't exist, really, according to everything they know about tracked tractors and the physics of crawler design. The photos show a machine, bright green, absolutely massive, and it has two engines, side by side, two complete powertrains, two transmissions, two of everything. And it's not some cobbled together prototype, some backyard inventor's fever dream. No, this thing is being mass produced by General Motors through their Euclid division. And worse, it's already out there, working, pushing dirt, making Caterpillar's largest dozer look, well, small. See, by the mid-1950s, Caterpillar owned the earth-moving world. They'd built that empire methodically, machine by machine, innovation by innovation. Their biggest crawler tractor at the time, the D8, was the king, around 230 horsepower, depending on the configuration. Tough as nails, proven, reliable. Everywhere you looked on a construction site, you saw that Caterpillar yellow. The company had become synonymous with heavy equipment itself. Then General Motors decided they wanted a piece of that action. Not just a piece, actually. They wanted to shake the entire industry, and they had the resources to do it. By 1955, GM wasn't just making cars. They were making, well, everything. Locomotives, diesel engines, heavy trucks, and through their Euclid division, they were making off-highway equipment. Dump trucks, scrapers, and now they were about to make the largest, most powerful production bulldozer the world had ever seen. The Euclid TC-12. And yeah, the name's pretty boring. No dramatic branding, no intimidating nickname, just TC-12. The TC stood for tracked crawler. The 12 indicated it was in the 12-ton drawbar pull class. Technical, straightforward, almost bureaucratic. But don't let that fool you, because this machine was anything but ordinary. Here's the thing that made the TC-12 so radical, so fundamentally different from every other dozer that came before it. Most crawler tractors, including all of Caterpillar's lineup, used a single engine mounted in the middle of the chassis, one power plant. That engine drove through a transmission to a final drive, and steering happened through clutches and brakes. You wanted to turn left, you'd reduce power or apply the brake to the left track while maintaining or increasing power to the right. Simple, proven, standard. Euclid's engineers looked at that approach and said, you know what, let's just not do that. Instead, let's build what is essentially two complete tractors side by side, connected by a central frame. Each side gets its own 194 horsepower Detroit diesel engine, each side gets its own transmission, each side gets its own final drive. Total system powerage? 388. That was more than 150 horsepower beyond anything Caterpillar offered. More than anyone offered, actually. And the steering system. Oh, the steering system. You didn't use clutches or brakes, you used the throttles. Want to turn left, you'd throttle back the left side while maintaining or increasing power on the right. Want to spin in place? Full forward throttle on one side, full reverse on the other. The machine would rotate on its own axis like a top. For such a massive piece of equipment, something that weighed in over 50,000 pounds depending on configuration, the maneuverability was shocking, almost unsettling to watch. Now, you might be thinking, okay, sure, but why would anyone build a machine this way? Two engines means twice the maintenance, twice the fuel consumption, twice the complexity. And you'd be right to think that. The TC-12 was complicated. It drank diesel fuel like a machine with two Detroit diesel two-stroke engines screaming at full throttle, which is exactly what it was doing most of the time. Fuel economy was not its strong suit, but there were advantages. Big ones. First, redundancy. If one engine failed, theoretically you could limp along on the other side, though in practice this wasn't really how it worked. More importantly, the dual power plant setup meant you could deliver massive amounts of power to the ground without needing to engineer some monstrous single engine and the equally monstrous transmission to handle it. You could use proven production engines, production transmissions, standard components, easier to source, easier to replace. And there was something else. Something that General Motors, Euclid's parent company, cared deeply about. The TC-12 showcased GM technology from end to end. Those Detroit diesel engines? GM. The design aesthetic, styled by Chuck Jordan, one of GM's automotive designers, the same guy who'd penned the wild Aerotrain locomotive and later become vice president of design for all of General Motors. Even the bright green paint, that distinctive Euclid green, it was part of their broader strategy to make their off-highway division as recognizable as their automotive brands. The machine made its very public debut at Powerama, GM's massive industrial exposition held on the Chicago lakefront in the late summer and fall of 1955. 2 million people attended that event. 2 million, and the TC-12 was there, center stage, performing demonstrations, tug-of-war competitions with elephants, precision driving exhibitions. It was part of what they called the world's first technological circus, and it stole the show. So the TC-12 hits the market in the mid-1950s, and the initial reaction from the industry is mixed. On one hand, you've got contractors who are looking at this thing and seeing possibilities. The sheer power meant you could push heavier loads. You could work in conditions where a single-engine machine would bog down or require helper dozers. The maneuverability, that ability to spin on its axis, that opened up working in tighter spaces than you'd expect for a machine this large. But on the other hand, there was skepticism. Deep skepticism. See, the construction and earth-moving industries are conservative by nature. Not politically, I mean, though maybe that too, but conservative in terms of adopting new technology. When you're running a job site, when you've got schedules and contracts and penalties for delays, you don't want surprises. You want proven equipment. You want something that your mechanics know how to fix. You want parts availability. You want to know that when you fire up that machine on Monday morning, it's going to run all week without drama. And here comes Euclid with this 2-engine contraption that fundamentally reworks how crawler tractors operate. The maintenance schedules alone were enough to make fleet managers nervous. You're not maintaining one engine, you're maintaining two. 2 sets of filters, 2 sets of fuel systems, 2 sets of cooling systems. Everything doubles. And those Detroit diesel 2-stroke engines, while powerful and relatively compact for their output, they had a reputation. They were loud, they were smoky when pushed hard, and they needed attention. But here's what shifted opinions. The TC-12 worked. Once contractors got past the initial hesitation, once they put the machine in the field and actually used it, they discovered that, yeah, the fuel consumption was brutal, but the productivity was remarkable. You could push scrapers that would overwhelm smaller machines. You could move earth faster, which on big projects meant finishing ahead of schedule, which meant moving on to the next job sooner, which meant more revenue. And the steering system, that throttle-controlled steering that seemed so unconventional, operators loved it. Once you got used to it, and apparently the learning curve wasn't that steep, you had finer control than you did with clutch and brake steering. You could position the machine more precisely. You could make adjustments on the fly without the jerky, abrupt movements that came from braking one track. It felt more like driving, less like wrestling. Caterpillar, meanwhile, was paying very close attention. They'd initially dismissed the TC-12 as a niche product, something that might appeal to specific applications but wouldn't threaten their market share. But as Euclid started placing these machines on high-profile projects, as word spread about the TC-12's capabilities, Caterpillar realized they had a problem. Not an existential crisis, but a legitimate competitive threat in the super-heavy crawler dozer category. The thing was, Caterpillar's entire design philosophy was built around single-engine configurations. Their engineering was optimized for it. Their manufacturing was set up for it. Their supply chains, their dealer networks, their training programs, everything assumed a conventional single-engine clutch and brake steering layout. Pivoting to match Euclid's approach would require massive investment and time they might not have if the TC-12 started seriously eating into their market share. So Caterpillar did what Caterpillar does best. They doubled down on their existing strengths. They worked on increasing power in their single-engine designs. They improved their transmissions. They enhanced their undercarriage components. And they leaned heavily on their dealer network, arguably the strongest in the industry, to emphasize the advantages of conventional designs. Proven technology, simpler maintenance, better parts availability. All true, all legitimate selling points. But they also, quietly, started R&D on larger machines, because the TC-12 had proven something important. There was demand for super-heavy crawler tractors. The construction industry was tackling bigger projects. Interstate highway construction was ramping up. Dam building, strip mining, open-pit mining. These applications needed massive machines, and contractors were willing to pay for that capability. Now, let's talk about what the TC-12 actually looked like in the field, because pictures and specifications only tell part of the story. This machine, when you stood next to it, was imposing. The two exhaust stacks, one for each engine, rising up on either side. The operator station, sitting high above the ground, giving the driver a commanding view. And the noise. Oh, the noise. Those two Detroit diesel two-strokes, when they were both at full throttle, they produced this distinctive sound. Not quite a roar, more like a sustained mechanical scream. You could hear a TC-12 working from miles away. The blade configurations varied depending on the application. Euclid offered straight blades, angle blades, and U-blades. The largest U-blade setup, which was designed for moving maximum material, was enormous. Just the blade itself weighed several thousand pounds. When you added that to the front of the machine, along with the hydraulic cylinders to control it, you were looking at a package that could move serious volumes of earth in a single pass. But here's where things get interesting from an engineering standpoint. The TC-12's dual engine setup meant that weight distribution was actually more challenging than on a conventional Dozer. You had two heavy engines, one on each side, the fuel tanks had to be positioned to maintain balance, the operator station, the blade, the ripper if equipped, everything had to be carefully located to keep the center of gravity where it needed to be. Get it wrong, and the machine would be unstable. It might try to tip on side slopes. It might not track straight under load. Euclid's engineers solved this through careful frame design. That central connecting structure, the backbone that tied the two independent crawler units together, was heavily engineered. It had to be rigid enough to keep everything aligned, but it also had to flex slightly to allow the tracks to conform to uneven ground. Too rigid, and the whole machine would lift off the surface when working on rough terrain, losing traction. Too flexible, and the whole machine would twist itself apart under load. The tracks themselves were another challenge. Standard Dozer tracks are designed for a certain power level, a certain load capacity. The TC-12 was pushing beyond those limits. Euclid had to develop heavier track lengths, stronger pins, more robust rollers and idlers. The undercarriage on a TC-12 was built like you'd expect on a machine twice its size, because in terms of the forces it was generating, it basically was a machine twice its size. Now, as the TC-12 gained traction in the marketplace, pun absolutely intended, Euclid found itself in an interesting position. They had a hit product. Contractors wanted it, but producing the TC-12 at scale presented challenges that went beyond normal manufacturing concerns. Remember, this wasn't just building more of the same. Each machine required two complete powertrains, precisely matched and synchronized. Quality control was critical. If one side was even slightly more powerful than the other, the machine would pull to one side under load. Not ideal when you're trying to push a straight cut. And there was the supply chain complexity. Euclid needed a steady flow of Detroit diesel engines from GM's engine division. They needed transmissions, final drives, track components, hydraulic systems. Any bottleneck in that supply chain would shut down TC-12 production. And this was the 1950s. Just-in-time manufacturing didn't exist. Computer-controlled inventory systems didn't exist. You managed your supply chain with phone calls, telegrams, and a whole lot of manual coordination. But here's what Euclid had going for them. They were part of General Motors, and GM in the mid-1950s was the most powerful industrial corporation on Earth. They had resources, they had manufacturing expertise, they had logistics networks. When Euclid needed engines, they got engines. When they needed engineering support, they got GM's best engineers. That backing, that institutional support, it meant Euclid could punch above their weight in ways that an independent equipment manufacturer simply couldn't. The TC-12 evolved over its production life. Early machines, the ones that debuted around 1955, they had certain characteristics and limitations. The engines were naturally aspirated Detroit diesel 271s, meaning each cylinder displaced 71 cubic inches, 4 cylinders per engine, so 284 cubic inches per power unit. Not huge by modern standards, but remember, 2-stroke diesels produce power differently than 4 strokes. Every piston stroke is a power stroke. That's why they could generate 194 horsepower from relatively small displacement. Later TC-12 variants incorporated improvements. Turbocharging became available, boosting power output significantly. Upgraded transmissions handled the increased torque. The hydraulic systems for blade control became more sophisticated, giving operators finer control and faster cycle times. The operator stations improved, with better visibility, more ergonomic controls, actual weather protection instead of just a rolled piece of canvas. And the machines got used hard. Strip mining operations in Appalachia ran TC-12s around the clock, pushing overburden, creating benches, moving millions of tons of material. Highway construction crews used them to clear right-of-way, excavate cuts, push dirt for embankments. In the western states, where large-scale irrigation and water management projects were underway, TC-12s shaped the land, built levees, excavated channels. The military took interest too. The U.S. Army Corps of Engineers evaluated the TC-12 for potential use in rapid airfield construction and combat engineering applications. The power and productivity were attractive, the fuel consumption and maintenance requirements less so. But the evaluation itself, the fact that the military was looking seriously at these machines, that gave Euclid credibility. It signaled that the TC-12 was more than just a commercial experiment. By the early 1960s, Caterpillar had responded with their own super-heavy offerings. The D9, introduced in 1955, was their answer to the growing demand for larger machines. It was still a single-engine design, conventional clutch and brake steering, but it packed significantly more power than the D8 it supplemented. Around 380 horsepower, depending on configuration, right in the same ballpark as the TC-12. The competition between Euclid and Caterpillar became intense. On job sites, you'd see both machines working side by side, and contractors would compare productivity, reliability, fuel consumption, operator preference. Trade magazines ran comparison articles, equipment dealers positioned their respective machines as superior, and both companies pushed their engineering teams to keep innovating. Euclid's challenge was that while the TC-12 was impressive, it was also expensive. Not just to buy, though that was part of it, but expensive to operate. Those twin Detroit diesels consumed fuel at a rate that made accountants wince. Maintenance was labor-intensive, and while the machine was reliable when properly maintained, the key word there is properly. Skip maintenance, run the machine too hard, ignore warning signs, and you could have expensive failures. Not catastrophic, not usually, but expensive enough to hurt profitability on a project. Caterpillar's conventional designs, meanwhile, benefited from decades of refinement. Their single-engine approach was well understood. Mechanics knew how to work on them. Parts were everywhere. Fuel consumption, while never good on any heavy dozer, was better than the TC-12s. And as Caterpillar continued developing their D9 and later even larger models, they were closing the performance gap while maintaining their operational advantages. By the mid to late 1960s, market dynamics were shifting. Euclid's parent company, General Motors, was reassessing its off-highway equipment strategy. The earth-moving equipment business was profitable, but it required constant investment. New model development, manufacturing capacity, dealer support, and GM, facing increasing competition in the automotive market, was looking hard at where they allocated capital. In 1968, GM made a decision that would reshape the earth-moving equipment industry. They sold the Euclid division to White Motor Corporation. Not the entire Euclid division, actually. There were antitrust complications because White already owned some earth-moving equipment operations, so GM had to divest certain product lines. It got complicated. Corporate lawyers got rich, but the outcome was that the Euclid name, along with many of their products, moved out of GM's control. The TC-12 by this point was aging, not obsolete, but no longer the revolutionary machine it had been in 1955. Newer designs from multiple manufacturers were matching or exceeding its capabilities with more conventional, easier-to-maintain configurations. Production wound down. Exact end dates are murky, the records aren't perfectly clear, but by the early 1970s, new TC-12s were no longer being built.
So what happened to all these TC-12s? Because unlike cars, which might get crushed when they're worn out, heavy equipment often has a very different life cycle. When a big dozer reaches the end of its useful life with its original owner, it doesn't necessarily end up in a scrapyard. It gets sold. Third party, fourth party. It migrates down through different levels of contractors. Maybe it goes overseas to developing countries where labor is cheap and keeping old equipment running is economically viable. Many TC-12s followed exactly that path. After their first lives with major contractors on big American projects, they'd get sold to smaller operators, regional contractors, rural operators who needed heavy power but couldn't justify or afford newer equipment. These machines would get run hard, repaired repeatedly, and kept working for decades beyond their original expected service life. And repairs on a TC-12, well, they could be adventures. Finding parts for a machine that hadn't been manufactured in years, that was always a challenge. But here's where the Detroit diesel engines actually became an advantage. Those engines were used in everything. Trucks, buses, generators, marine applications. So even when Euclid-specific parts became scarce, you could still get engine components. Pistons, injectors, bearings. The core power plant could be kept running through sheer determination and parts sourcing creativity. Some TC-12s ended up in museums and equipment collections, because even as working machines, they'd become historical artifacts, examples of a particular approach to crawler tractor design, a moment when manufacturers were experimenting with radical alternatives to conventional configurations. Equipment preservation groups, the kind of people who restore old machinery the way others restore classic cars, they saved a handful of TC-12s. If you're lucky, if you attend the right old equipment shows, you might see one running today. And let me tell you, seeing a TC-12 fired up, both Detroit diesels running, that's an experience. The sound alone is worth the trip. That distinctive two-stroke scream, multiplied by 2, echoing across a field. The smoke, because two-stroke Detroits always make some smoke when they're working. The raw mechanical presence of the thing. It's a window into a different era of engineering, when bigger meant literally bolting two machines together and seeing if it worked. The broader story of the TC-12, though, it's really about experimentation and the nature of industrial innovation. See, Euclid's engineers weren't wrong to design the machine the way they did. The dual-engine configurations solved real problems. It delivered capabilities that contractors needed. It worked. But working isn't the same as optimal. And in the competitive heavy equipment market, optimal matters. Fuel efficiency matters. Maintenance simplicity matters. Parts availability matters. Caterpillar's eventual dominance in the super heavy dozer category came not because they built some revolutionary new design, but because they refined their conventional approach to the point where it matched the TC-12's capabilities without its drawbacks. They developed larger, single engines that produced comparable power. They improved their transmissions and final drives to handle the increased torque. They enhanced their undercarriages to support heavier loads. All evolutionary, not revolutionary, but evolution won. There's a lesson there, maybe, about the tension between radical innovation and incremental improvement. The TC-12 was radical. It challenged assumptions. It proved that unconventional designs could work in production, could find market acceptance, could generate profits. But the radical approach also had inherent compromises. And while Euclid was managing those compromises, their competitors were busy eliminating the need for compromise through steady refinement of existing technology. Another factor was corporate strategy. Euclid, as part of General Motors, had access to resources and expertise that few competitors could match, but that also meant they were subject to GM's broader corporate priorities. When GM decided the off-highway equipment business wasn't core to their future, when they chose to divest Euclid, that strategic decision impacted every product line, including the TC-12. The machine's fate wasn't killed by engineering failure, it was killed by business strategy. Or more accurately, it was allowed to age out without replacement because the new corporate owners had different priorities. The TC-12's influence did continue, though, in subtle ways. The concept of using twin power plants on heavy equipment didn't die completely. Much later, some mining equipment manufacturers would revisit dual-engine configurations for ultra-heavy applications where a single engine simply couldn't deliver sufficient power in a manageable package. The steering concepts, throttle-based control, that showed up in hydrostatic drives that became common on smaller equipment. Ideas don't disappear. They evolve. They get adapted. They reappear in different forms when the technology and the market conditions align. And there's something to be said for the sheer ambition of the TC-12. In an era when most manufacturers were making incremental improvements to established designs, Euclid built something fundamentally different. They took a risk. They invested in tooling, in development, in production capacity for a machine that had no proven market. That takes confidence. Or maybe hubris. The line between them is only visible in hindsight.
So here we are, looking back at the Euclid TC-12 from the perspective of 70 years. And what's clear is that this machine, this twin-engined monster that was supposed to revolutionize crawler tractor design, it didn't revolutionize anything. It didn't reshape the industry. It didn't force competitors to abandon their conventional designs and follow Euclid's lead. But that doesn't mean it failed.
Because failure and success in industrial equipment aren't binary outcomes. They're complex, multifaceted evaluations that change depending on what you're measuring. From a pure engineering standpoint, the TC-12 succeeded. It proved that a dual-engine configuration could work in a production machine. It delivered the performance Euclid promised. It found buyers. It generated revenue. It worked on job sites without being a constant disaster. That's not nothing. That's actually a lot, given how many ambitious engineering projects collapse under the weight of their own complexity. From a market standpoint, it's more ambiguous. The TC-12 carved out a niche. It gave Euclid a presence in the super-heavy Dozer category. It forced competitors to pay attention, to respond, to accelerate their own development programs. But it never achieved dominant market share. It never became the default choice. And ultimately, it was displaced by more conventional designs that offered similar capabilities with fewer operational complications. From a business standpoint, well, that's where things get murky. We don't have perfect financial data. We don't know exactly how profitable the TC-12 was for Euclid over its production life. We know it required significant investment to develop and manufacture. We know it sold in meaningful numbers, but not overwhelming numbers. And we know that when GM divested Euclid, the TC-12 product line didn't long survive that transition. Make of that what you will. But here's what's interesting. The TC-12 is remembered. In equipment collecting circles, among historians of construction equipment, in forums where old machinery gets discussed and debated, the TC-12 has a reputation. It's remembered as the weird one, the experimental machine, the two-engine dozer that tried to do things differently. And there's value in being remembered, even if you're remembered for being unconventional. Today's crawler tractors, the massive D11s and Komatsu 970s and other super heavy dozers, they're all single-engine machines. They all use conventional steering methods, though now they're sophisticated hydraulic systems instead of clutches and brakes. The TC-12's specific design approach didn't win, but the capabilities it demonstrated, the demand it proved existed for ultra-heavy machines, that shaped how the industry developed. Caterpillar might have eventually built bigger dozers anyway, but the TC-12 accelerated that timeline. It provided competitive pressure. It showed contractors that massive productivity was possible if you had the right equipment. And there's something wonderfully audacious about the whole TC-12 story. In an industry dominated by one massive incumbent, Caterpillar, a competitor tried something radical. They didn't just build a slightly better version of what everyone else was building, they fundamentally rethought the design. They said, what if we just used two of everything? And they built it, and it worked. Not perfectly, not optimally, but it worked. That kind of willingness to experiment, to take risks, to challenge conventional wisdom, that's rare in heavy industry. The capital requirements are enormous, the development timelines are long, the markets are conservative. It's much safer, much more sensible to make incremental improvements to proven designs. But occasionally, someone decides safe isn't good enough. Someone decides to try something different. And even when those experiments don't succeed in changing the world, they make the world more interesting. So the next time you see a bulldozer working, pushing earth, shaping the land, think about the TC-12. Think about the engineers who looked at the conventional single-engine design and thought, we can do this differently. Think about the operators who climbed into those machines and learned to steer with throttles instead of clutches. Think about the contractors who took a chance on unconventional technology because they needed the productivity it promised. Think about the mechanics who kept those twin Detroit diesels running, who sourced parts, who solved problems, who made the machine work day after day on job sites across the country. The TC-12 didn't change heavy equipment forever, but for a while, for a brief moment in the 1950s and 60s, it showed that change was possible, that the established way of doing things wasn't the only way, that with enough engineering skill and corporate backing and sheer determination, you could build something different, something bigger, something that made the competition nervous. And sometimes that making the competition nervous is its own reward, because it means you built something that mattered, something that couldn't be ignored, something that 70 years later people still talk about, still remember,
still get excited about when they see one running at an old equipment show, both engines screaming, tracks churning, pushing dirt like it's 1955 all over again, and anything is possible.